Welcome students. Now we are going to start with the next topic, that is the heat treatment. So heat treatment, in this video we are going to see the introduction about this topic and the first heat treatment process, that is the hardening. So dear student, the engineering properties of the most of the metals and alloys is basically depend upon the structure of the material, and if we practically vary the properties of micro constituents material of the material, we can change the mechanical properties. So basically, to change the mechanical properties, we are having the process called as the heat treatment, isn't it? And it is process in which we are heating the specimen, holding it for particular time period, and with certain cooling rates we are cooling it. And please remember that we are doing this treatment on the solid phase of the specimen, isn't it? So there should be shaped object. So the liquid is not allowed. We have the solid shaped object. On that only we are doing this heat treatment process, isn't it? So if you talk about again for the heat treatment, it is basically the secondary process where we are working on the solid phase of the material without changing the chemical composition. Please remember, here with the specimen, object or material, whatever we are taking for the process, we are not going to change, we are not going to interrupt for the chemical composition of that specimen, but yes, of course we are interested to change the grain structure of that material, so that, because as we know, the theme of material science is what? When we change the crystal structure or structure of the material, we can see the change in mechanical properties. So we are dealing with only grain size structure or grain structure to have this heat treatment process. Now dear students, what is the purpose of this heat treatment? What the benefits, what the advantages that we can get? If we write here, the name of the topic is what? Heat treatment. Heat treatment. Let us point out the important notes here. Okay, so here the very important, the theme of material science is what? Material properties are depend upon what? The structure of the material, isn't it? Second thing is what? If we practically varied the properties of micro constituents, we can change the mechanical properties. And third thing is what? That here we are doing this heat treatment in such a manner that we are heating, holding or soaking, also it is called as soaking, and cooling the specimen to get the desired properties into the material, isn't it? Then very importantly, what? We are not changing the chemical composition. So what we are going to have here? Only the change in grain structure, very important. Change in grain structure. And very importantly, on solids we are going to perform it, isn't it? The material should be in solid stage or solid phase, I can write here. Very important. So shaped object should be there for this treatment. If you look at the basic purpose of this heat treatment, so what we are going to get actually. So dear students, when we imply these heat treatment processes on this specimen of the components, we can get the required ductility of the material. We can improve the machinability of that specimen. We can improve the strength or hardness of that specimen. We can have the refinement of the grains for that material. Then we can change the magnetic and electric properties, isn't it? And we can also have we can make this material available for further processing, for the secondary processes after the heat treatment. So these are very important, like we can have the improvement in the ductility, improvement in the machinability, the strength, hardness, then we can have the refinement of the grain sizes. Like that we can get the benefits from this heat treatment process. Now dear students, if we look the steps in the heat treatment, the heat treatment is basically done in 3 steps. So already we written here, see, first step is heating of that specimen, second is holding or soaking, and third is cooling, isn't it? So let us see that. So dear students, if you look at the steps, we are having first the heating. So dear students, in this process we are heating the given specimen at certain temperature, isn't it? And this temperature, basically at what temperature that we are going to heat. So suppose if I take the example of steel, the heat treatment in the steel, so definitely the temperature up to which the specimen can be heated is determined from the iron and iron carbide equilibrium diagram. So as the heating temperature is important, in same fashion the heating rate, at what rate you are heating the specimen, this is also important, please remember. So here the specimen is heated up to certain temperature. And example, if you take the steels, for steels this temperature is written from Fe, Fe3C, isn't it? This diagram, Fe3C equilibrium diagram or phase diagram, isn't it? Then at what rate you are heating? Heating rate is also very important. Heating rate is also important. So based upon say the shape, size and the thermal conductivity of the object, we can select the temperature, at up to what temperature we can heat that specimen. Now dear students, in this first step what is going to happen with the specimen, क्या होगा उसके साथ? So when we heat the material at particular or certain temperature, so there will be very important 2 things happening. That is, the first thing, there are relieving of internal residual stresses. And second thing is going to happen is that there will be the enlargement of the grains, please remember. So in the heating step, which 2 important things that going to happen with this specimen, that heat is going to relieve the internal stresses in that material, internal residual stresses, because of some working, because of casting, solidification, because of welding, blah blah, whatever the process that is had. So it will relieve that stresses. And the second thing is that the enlargement in this grain. Okay, so this is actually happening with the heating. Let us see about the holding or soaking. The second one is holding or soaking. So after heating, the specimen is held for or soaked for particular time period. Okay, and this time period actually for some time. See, after, if you look at the cycle, this is the temperature and this is the time. So initially we heat the specimen, isn't it? Now we are holding it. So it was a heating, isn't it? Now this is the holding for particular amount of time based upon the requirements. Okay, generally see this holding basically holding time period is basically depend upon the object, isn't it? So if we look at the generally, we are having this holding is 2 to 3 minutes for every 1 millimeter. For every, I will write here, for every 1 millimeter of the section thickness of the object. Please remember, for every 1 millimeter section thickness of the object, we are having this holding time around 2 to 3 minutes, isn't it? So this is how we can have this holding time or soaking time. So here what is going to happen, what we are going to see in the structure of this object. So here with this soaking or this holding time period, the grains are becoming uniform. The grains become uniform. You will get the uniformity in the grains, isn't it? So this is going to happen in the holding time period. And after holding, we have to cool that specimen with a certain cooling rate. Let us see. Then third is cooling. So dear students, please remember that the mode of cooling, the mode and the mode of rate of cooling. I will write the mode of cooling and the rate of cooling depends upon the factor which decides the mode of heating and rate of heating. Please remember this, and rate of heating, isn't it? So as we can see, there are the various observations that we have when we are cooling the micro constituents of the material with the different cooling rates. So see, either we can have the slow cooling rate, or we can have the fast cooling rate. So the slower rate cooling rate, what it possesses? Okay, and the fast cooling rate, what does it possess? Isn't it? So let us see, when we are cooling this specimen with the very slow cooling rates, so what thing we are going to get here? We are going to get here, that is the coarse grain structure. First thing is what? Please remember, when we cool with the very slow cooling rates, we are going to get the coarse grain structure. Then we can have the improvement in ductility and toughness. And third thing, we are removing the internal residual stresses. So when we are cooling with very slow cooling rates, we are getting this actually advantages. You can say these things we are going to get with this slow cooling rate. And when we are having this cooling rate as fast cooling rates, so definitely we are going to get the fine grain size or grain structure, which will increase in the strength and hardness, please remember. And but it is decreasing what? The say machinability. So these are the things we are observed when we cool with the slow cooling rate and we cool with the fast cooling rate, isn't it? So diagrammatically, if you want to see this, so dear students, if you're going to see diagrammatically how these three steps can be done in the heat treatment. So say after heating, I am showing here this picture of our microstructure. So when the heating of this specimen, what we are going to have, there will be the relieving of this internal residual stresses and the enlargement of grain structure, isn't it? So when this heating is completed, we are going to have the holding or soaking, so where we are going to get the uniform grain size, isn't it? And when we cool it with the two cooling rates, slow cooling is there and fast cooling is there. So slow cooling will have the coarse grain structure. So if I show the uniformity in the grain like this, so little bit for, so you are getting a big grains here, isn't it? And when this fast cooling is there, we can have the fine grains, isn't it? So this is the coarse grains having good ductility, having good machinability, having good toughness, and these are the fine grains having good strength, hardness, isn't it? But low toughness and low ductility. So like that we can have the structure, grain structure after cooling. So after this, students, we are going to see the first heat treatment process, that is hardenability. Let us see. Dear students, let us see this first heat treatment process, that is the hardening. So hardening is basically it is applicable for all these steels, low carbon steels, medium carbon steels, and also it is applicable for the high carbon steel. So basically the hardening process is used to increase the strength and hardness, of the steel specimen by rapidly cooling of this object or specimen, by rapidly cooling of object. Please remember, so very important, when we do the hardening, the strength and hardness of the steel is go on increasing. Now see, when we heat the steel, suppose if I am writing for the hypoeutectoid steel and the hypereutectoid steel, so we should heat the steel above 50 degrees centigrade of upper critical temperature for hypoeutectoid steel, and 50 degrees centigrade above the lower critical, that is lower critical temperature of the hypereutectoid steel, of the hypereutectoid steel. So if we plot this phase diagram, the part for this eutectoid reaction, eutectoid transformation, so we will have it like this. So suppose this is 0.025% carbon, this is 0.8%, this is 0.4%. And this is 723 degrees centigrade, that is the A2 line, this is A3 line, and here is gamma austenite from 723, above 723 up to 1910. The gamma austenite from it is above from this 910, so it is gamma, which is austenite. This is gamma plus Fe3C, this is alpha plus gamma, this is our alpha, and this is the alpha plus cementite. It's perlite, isn't it? So if you see here, this is 100% perlite, we know very well, 0.8% steel, this is weight percentage of carbon, isn't it? Now see here, if we see this range for the heating range, so we are heating the steel above 50 degrees centigrade, 50 degrees centigrade above this upper critical temperature. So upper critical temperature, this for the from, see, this is the region for the hypoeutectoid steel, isn't it? And up to 2% we are having 0.8 to 2.1%, that is hypereutectoid. So in hardening, we are heating the steel specimen 50 degrees centigrade above. See, this is the upper critical temperature for this hypoeutectoid steel, and this is the lower critical temperature. This is the lower critical temperature line, and this is the upper critical temperature line. So this is A2 line, this is A3 line, and this is the ACM line, last trace of cementite. This is the last trace of ferrite, and this is A2 line, isn't it? So see here, if you see this hardening temperature range, so if I take the low carbon steel, say I'll take from 0.4%, so it will look like this. So this is the range for, this is the temperature range for hardening process, isn't it? So we are heating, see, 50 degrees centigrade above this upper critical temperature for hypoeutectoid steels, and for hypereutectoid steels, this above this A2 line or 723 degrees centigrade, that is a lower critical temperature, above that 50 degrees centigrade. So this is actually temperature range for the hardening process for hypo and hypereutectoid steels. So after heating, what we are doing? We are rapidly quenching. We are rapidly quenching these heated specimen, into water bath or oil bath or water salt bath. And when we directly quench this specimen, what is going to obtain there? So we are getting which structure? Martensite is going to form, which will results into martensite, isn't it? So which structure that we are going to get when we rapidly quench this specimen into the salt bath, water bath or oil bath? So we are going to get the martensite. And see, the formation of this martensite, or if you see the hardness of this martensite, is depend on the percentage of composition, where how much percentage carbon is there. So if you see at 0.8 percentage of carbon, the hardness of the martensite at 0.8 percentage of carbon on Rockwell C scale, it is 66 HRC, hardness on Rockwell C scale, isn't it? So this is actually the process. It is a hardening process where we are increasing the strength and hardness of this steel specimen. But see here, after getting this cooled in this water bath or salt bath, what we are getting? The martensite, isn't it? And you know the structure of the martensite is what? It is body centered tetragonal structure. What is the structure of the martensite? It is BCT. Okay, now which properties that we are going to get in the hardened component? So see, hardened component, what we'll get? So definitely the strength and hardness is increased. Second, there is reduction in what? Machinability. Please remember, reduction in the machinability. And third very important thing is that there is increased in residual stresses. Okay, now see here, when this martensite is the product of the rapid quenching of this steel specimen, as we know that this martensite is what? It's very hard and brittle. So we cannot use this martensitic structure of this specimen for these engineering applications. So definitely the hardened component has to give some subsequent heat treatment process, and that heat treatment process is actually known as the tempering, to give the softness, to give some ductility and machinability for the steels. We are doing that tempering process. So that is very important thing. Directly hardened component we are not using as it is for this engineering applications. Now see here, so here we are having this residual stresses, or I can say the residual strains in the hardening. What is the reason? So basically see, as we are heating the steel from the austenitic region to the directly quenching, means what? We are taking it to the room temperature. So as a result, from this austenitic range, so here is austenite, and we are directly quenching it to room temperature, and we have got this needle like structure as a martensite, isn't it? Now see, this austenite is getting converted into what? The martensite. But if you look at this hardened component, the core of this component is containing some amount of the retained austenite, and this is the hardened depth, what I am showing with this hatched line. This is the martensite. So what does it mean actually? So when you quench in this salt bath, this martensite, because see, it is very rapid process, so very fast you have taken this austenite from its temperature, austenitic temperature, to the room temperature. So whatever the conversion of austenite is taking place into the martensite is not up to the full depth of the object, because the core is not getting that much time to get converted into martensite because of the rapid cooling. So that is the reason why some austenite is get retained into this core of this object. Please remember here, because very fastly in shorter period of time you have quenched it from this austenite to the room temperature. So definitely, because whichever the time it get, only martensite is formed, but the core of the object is still not get 100% converted into martensite. So this is the retained austenite. So definitely, if you can observe here, this is a single object or single specimen. Within that, if you see the martensite, it's a very hard and brittle phase, isn't it? And compared to that, this retained austenite, isn't it? So it is, compared to that, it is softer phase, isn't it? And it is trying to expand. It is trying to expand, whereas martensite, because of this quenching, it is trying to contract, isn't it? So martensite is contracting, and this retained austenite is trying to expand. So it is trying to expand, whereas martensite try to contract because of the cooling, because of the quenching, rapid cooling, isn't it? So because of this, so core of the object is expanding, whereas the outer of the object is contracting. That is the reason why the huge amount of hardening strain, I have written here. So huge amount of hardening strain is produced during this hardening operation. Please remember, this internal residual stresses that we are talking about, these are the stresses, internal strains, which are there without any external stresses. Please remember, what are these internal residual stresses? These are the stresses like this. We are not applying any kind of stress, any kind of load on that, but still they are getting produced in the material. So these are therefore known as internal residual stresses. Okay, so one thing is very important about this retained austenite. Now see, if you increase, if you want to find out the depth of hardenability, that is from the skin or from the outer surface, up to how much depth the workpiece has get hardened, that is up to how much depth the martensite is get produced, so that is known as depth of hardenability, isn't it? So I will write it as DH, depth of hardenability. So if you see here, this is the object, and up to this much depth we have get the surface as hardened surface, or we have able to get the martensite up to this depth. So this is this hardenability depth, isn't it? So please remember that, see, depth of hardenability can be measured by the test known as the Jomini end quench test. Which test? Jomini end quench. So what is there actually in that test? So there is a Jomini round bar is there. So that round bar is heated up to the austenitic temperature, and we are fixing it, that bar, into the supporting pallet like this. This is a round bar of diameter 25 mm, which is placed in the supporting pallet. See, this is 25 mm. From the end of the rod up to this water, this is a water spray. This distance is 12.5 mm, and this distance is 100 mm. Okay, so in this test what is done? So in the supporting pallet, this is the supporting pallet, on which the round bar is placed here, and which is heated up to austenitic temperature, and now we are quenching it by having this water spray at this end of this bar, isn't it? And of course, for measuring this hardness, we are having the Rockwell hardness tester. We can measure the hardness of this specimen, isn't it? So we are quenching from this end. This bar is, sorry, we have this bar, heated bar up to austenitic region, and we are quenching this bar at the end by using this water spray, and simultaneously we are measuring the hardness, isn't it? So this is actually the Jomny end quench test, which can measure up to what depth the material become harder and stronger. That is how much depth the martensite has get formed into the given object by this hardenability, by this hardening process, isn't it? So please remember, many times for match the pairs question asked, that is the hardenability is measured by which test? So there is a Jomny and quench test is there, which I just now I explained. So dear students, this is the very important information about the first process that we are looking for, the hardening, where it is applicable for all the materials, where we are heating the material above 50 degrees centigrade from the lower critical temperature as well as from the upper critical temperature for the hypoeutectoid and hypereutectic steels. We are rapidly quenching it into the water bath, water, oil or salt bath, and definitely the phase we are getting after quenching is the martensite, which is very hard and brittle. We cannot directly use it, so we have to go for subsequent heat treatment process after hardening, that is the tempering, isn't it? So here that we have seen that the core is expanding, that is retained austenite is there, and the outer surface is contracting. Because of that, huge amount of residual strains or hardening strains are getting induced in the component, and of course to relieve that we have to go for subsequent heat treatment process. And after that, this test, this depth of hardening can be measured by what? The Jomny end quench test. Now if you see, definitely as the percentage of carbon, if you see here, if I am having the Jomny end quench test for 0.2% carbon and say for 1.4% carbon, so in low carbon steels this depth of hardenability is less, this is the DH, and for high carbon steels we are getting the maximum or highest depth of hardenability. So I can write from this depth of hardenability for high carbon steel is more than depth of hardenability for medium carbon steel is greater than depth of hardenability for low carbon steel. So this is one of the relation we can make. Okay, so thank you so much.